Right, so welcome everyone to this new video, and in this new video what we are going to talk about on the board is a problem of free fall. Now of course that seems like a very simple problem to look at, but what we are going to see is that this is not as simple as most of the time people try to present it. And one of the reasons why it's not that simple is because it's going to depend on what you choose as being the inertial frame of reference. In this particular case, we are looking at a free fall problem with zero initial velocity of a ball that we are dropping from a specific kind of height of a tower, for example, and we are going to look at, what we are expecting from the theory, given that we consider the geocentric frame as being inertial. Okay, so let's put things a little bit in context. Here we've got a line that represents the surface of the Earth, and here we've got a tower. You can imagine like pizza tower, whatever you want, some kind of high tower. And then we've got a ball B that we drop with zero velocity relative to basically the top corner here, top left corner of this particular tower. And I put a point of reference O at that particular corner, and basically the tower here is of height h, and that's it. So that's the question we're asking. There is, of course, this is on Earth, so the ball is subject to the weight on Earth, and apart from that we are neglecting any sort of friction from the air and so on. Okay, we can also work this out later, but at least for now we just keep it like this. So traditionally, if you see that, and in fact if you ask ChatGPT, and if you say, oh ChatGPT, by the way, what happens if I drop a ball with zero velocity relative to let's say the tower I drop it from, and basically it's subject to its own weight, what you are going to get as an answer in like all physics textbooks is clearly from high school, A level in the UK, from ChatGPT and from most resources online, is basically that you've got a vertical drop of the ball, and there you go, that's it, like just a vertical drop, and then you can evaluate or calculate the time it takes to actually reach the ground, for example. Okay, now it turns out that this works if you consider the so-called terrestrial frame as being inertial. Okay, so the terrestrial frame is basically made of the surface of the Earth and then a local essentially set of axes which is kind of moving with the point, any point you follow on Earth. Okay, so that would be basically the terrestrial frame, and if you assume that to be indeed inertial, that's the answer you get. Now the question is, okay, if we assume instead of the terrestrial frame, we assume the geocentric frame to be inertial, then what happens? That's what we want to ask. So in the geocentric frame, here I'm going to exaggerate on purpose the drawings, but in the geocentric frame, what you have is that this flat portion here turns out to be simply, a sort of course here this is flattened a bit, but you need to imagine that this is basically a portion of a circle. Okay, so essentially this is the Earth. Okay, so the whole thing here is the Earth, and then you've got the center of the Earth here, and what happens is that you've got rotation omega of the Earth that is spinning here, and you've got a set of axes that are fixed like this. So you've got, let's say, x, y, and z. X, y, and then you may have z as well. Okay, so that's what you actually get, and then what happens is that because there is omega here, if you want to know the velocity of a point here, which is radially away from the center here, you actually need to know the distance. Okay, so the assumption is that this tower here is a rigid tower, so the angular velocity omega of a point at the base of the tower is the same as the angular velocity at the top of the tower. So that's the assumption we are going to make here. However, what happens and what it means is that the velocity of a point, the velocity, not the angular velocity, the velocity of a point at the base of the tower is actually different from the velocity at the top of the tower. And the reason why is because if you want to find out the velocity, v, so the magnitude of the velocity v of a point anywhere here is going to be equal to r and then times omega. So it's omega, the angular frequency, times r, which is the distance, the radial distance away from the point you're looking at. Okay? So what happens here is that I'm going to say that the distance from the center of the Earth to that point is actually the radius of the Earth. Okay? And then what we have is that we have that the velocity of point O in the x direction, okay, in the x direction, so here I'm assuming that I'm in a sort of locally vertical direction, Vox is equal to, and here again that's the magnitude, is going to be equal to Re plus H and then V. And then omega, that's omega I wanted to put here. Times omega in this geocentric frame, okay? And then what we are going to have is that we are going to have that V, and then I need to put another name here, so let's call this point O prime at the base. So we've got V O prime x is equal to Re and then times omega. Okay? So what we are going to look, because we want to know the trajectory essentially of the ball relative to actually O prime, because we want to know where the ball is actually landing on the ground. Okay? So what we are going to look here is we are going to look at things from the point of view of O prime. So what we are going to find is that the velocity, I'm not too sure how to put it exactly, but the velocity x, and I'm going to write here of point O relative to O prime, so that's the way I kind of describe it, so that the velocity in the x direction of O relative to O prime is going to be that minus that. Okay, so that's Re plus H omega minus Re omega. And again, that's the magnitude. So what you are going to find is that this is equal to H times omega. And just for the sake of it, if you put, for example, that H is like 90 meters, which is like a standard kind of relatively high tower, then you're going to get, in terms of numbers, if you are on Earth at the equator, you're going to find something along the lines of 6.5 and then times 10 to the minus 3 meters per second. Okay, so that's the actual velocity in the x direction, the magnitude of the velocity in the x direction. And actually, because omega is in that way, so there's going to be a minus value. So let's actually put minus here and minus here. Okay, so so that's basically what, that's really the ground thing to remember, is that because you want to know what is the trajectory of the object here that would be as seen from that particular viewpoint, then you're going to see that this is that there is a difference in velocity between the base and this part. Okay. So that's one thing. Then the other thing is that what you're going to find is that you can also solve. So you can say so the ball is only subject to its own weight. Okay, and so you're going to find, so because the geocentric frame is here inertial, you're going to find something like this. So so you're going to find MA is equal to F, and basically that's equal to minus mg in the y direction. So here these are the y with a hat is a unit vector that points in the y direction, and so this is going to lead you to the traditional a is equal to minus g, and a is equal to y dot dot, so the second derivative of y with respect to time is minus g. So from this you're going to get that y, assuming the point O actually is serve as reference, you're going to find that this is, well, let's actually that this is h, and then minus half g, and then t squared. So that's the traditional thing. Many people in Anglo-Saxon textbooks would probably use directly kind of the Suvat equations that are kinematic equations in the case of free fall. But in our case, we are going to use that. And so what we get from it is that the time it takes for this to reach the ground is going to be 2h over g, and then square root of this. Okay? Now, if you plug in the numbers again, so here g, I've taken something about 9.8 or something, but what you're going to get with again 90 meters for h. So here I should put actually with h is equal to 90 meters. Here you're going to find 4.3 seconds. So because the ball is only subject to the weight that is going in the y direction for this kind of very short motion here on Earth, then so that's a kind of 1 point, that's another one. Then what we are going to get as well is that the x displacement, so we are going to get x is simply equal to v x of o prime, and then times t. Okay, so the displacement in the x direction is equal to the difference between in velocity between o and o prime, and then multiplied by t. So what we are going to get if we basically multiply this number with this one is essentially approximately minus 3 centimeters. So what happens is that although as this moves and the tower actually moves as well, okay, so the tower moves, it's not, there is no ambiguity about this, the tower is going to move. However, because the ball maintains throughout the fall, maintains this velocity which was there and which was higher than actually this one, then the trajectory is going to look like this. Okay, and remember that at no point, so that's the ball here that I'm dropping, I should have actually put something like this, and the value you're going to find here for this particular thing is 3 centimeters. And again, it goes in the direction of rotation of the Earth. So usually that's what people call the eastward deviation. And so notice that in this particular depiction, I have no imagine like that the person was throwing the ball. The person is dropping the ball from this particular top of the tower, but the difference in velocity, because they are on a rotating object, which is the Earth, in the geocentric frame, basically you are going to get that. So you see that this is just 90 meters, so it's not like super tall, and that's enough in principle to actually get a difference of 3 centimeters, which is actually quite big and in principle at least measurable. So essentially that's just what I wanted to cover. There are more fancy ways of getting these kind of results, but this one, in my view, is the simplest way to understand what's really happening. Okay, in a future video, we are going to see how basically we can work this out a bit more mathematically, technically, and without using this kind of here relative velocity kind of right away. We are going to see how these things unfold, but in a more technical jargon and for a more general case like this. Okay, so if you've got any comments or questions on this, please do let them in the comment section or whatever it's called, and basically see you in the next video.